I received a question about the polar form of complex numbers. I think you're probably familiar with the rectangular form, but you can easily convert it to polar, and there's some advantages to the polar form, particularly when it comes to doing multiplication and or division, and even raising things to a power. It's a little bit easier in polar form. So let's talk about this real quickly. One thing that I hope is in your head about complex numbers, and the thing about complex numbers is they're really just a trick for doing computations in solving, later on we'll see, to solve differential equations. Okay, so if I was going to plot z1, I could use the real axis and an imaginary axis. And if z1 is 4 plus j3, I would go over and I'd count 4 for the real part. And then j3 is the imaginary part. And this would make a point in the complex plane. Okay, so maybe I mark that in red. Okay, here's the point. Well, I could also look at the length from the origin and call that a radius r, and I could measure an angle theta. All right, so I could represent z1 as r e to the j theta, okay, because the complex e to the jx is cosine of x plus j sine x. All right, so if you do the trig on that, you get, here's the cosine part and here's the sine part. Okay, so that's the exponential form. It looks like r e to the j theta. Now the thing is, theta needs to be in radians for this to work in computations that you do in MATLAB or on the computer. All right, so if I write down a number in polar form like z2, I wrote down 2 e to the j 45, and then I put the degree symbol. Okay, so the degree symbol simply informs us that this is in degrees, and if I wanted to actually calculate this number, I would need to put it back into radians. Okay, I could also graph z2. All right, so let me draw an axis here. All right, here's the real part, here's the imaginary part. And if I was going to graph this, I would go a length of 2, right? And then the angle would be 45 degrees, which of course is pi over 4. All right, so there you go. Now, if I wanted to convert z1 into the polar form, I can just use trig to get that done, and I would know that r, the radius r, is going to be 4 squared plus the imaginary part. So when you take the imaginary part, you don't include the j, you just take the number, all right? So the 3, and you square that, and then take the square root, all right? And to get the theta, it's just an arctangent of the imaginary part over the real part. And you have to keep track of quadrants if some of the angles are negative, and that's why you tend to use MATLAB to make these conversions. All right, so in MATLAB, I could come up with a command, and I could get r to be ABS, absolute value, of 4 plus j3. If I type that in, I would get the value of r. And if I wanted the angle, I would just, maybe say theta is equal to the A tan. No, I wouldn't do that. I would use the angle function because that takes care of all the quadrants. Okay, so angle of 4 plus j3 would give you back the theta. Okay, so the advantage of the polar form is that if I wanted to do division or multiplication, so let me go back to a black pen here. If I had z1 is equal to R1 e to the j theta 1, and I had Z2 is equal to R2 e to the j theta 2. So I'm kind of giving away an answer here, but if I wanted to find Z3, and it's the product of these two, well, the thing that happens is when you do the product, the radius, the two radii will multiply, and the two angles will add. Okay. Similarly, if you did division, the amplitudes, the absolute values will divide, and the angles will subtract. Okay. So hopefully that's enough of a hint to get you working through the polar form problems on the homework.